Hi, welcome, and thanks for tuning in here at P99 Conf. My name is Thorsten, and in this session we will talk through why WebAssembly is the key to build a fast, secure, and dense serverless platform. I work as a cloud advocate with Fermion Technologies, and my main job is to help developers to use latest and greatest technologies such as WebAssembly to build reliable, scalable, and modern things. For today's talk, I want to start with some serverless pain points. So things that we as developers may have discovered when building serverless applications. And the first thing I want to talk about is the dilemma of slow cold start times or the cold start delay. And it doesn't matter if you were using platforms like Azure Functions or AWS Lambda, you may have recognized those 200 to 600 milliseconds that your workload from time to time needs in order to start processing. And this is obviously annoying for us as developers and for our users, and a big pain point for those serverless platforms that we know as of today. If we move one step deeper in the stack, we may have containers. Although containers are great and they are very small compared to things like virtual machines, they are still big in size if we compare the actual size of our application to the size of the container image. A container image usually consists of the operating system, of additional frameworks, libraries, or even web servers. And those don't just sum up in size, they also make our distributable unit complex, right? We have to maintain all those bits and pieces of a container image, and we have to secure them. In order to address some of those shortcomings from containers, like their size and maybe, that underlying platform limitations that prevent us from scaling actually down to zero and scaling up to deal with unexpected load, we tend to use something that's called over-provisioning, where we keep instances of our containers running in order to handle load that may appear in the near future. So although this over-provisioning mechanism could address some of the shortcomings, we will end up with paying more for our application as actually would be required. Let's go one step deeper. If we take a look at orchestrators, like for example, Kubernetes, we may also encounter some pain points, like for example, workload right-sizing and demand-based downscaling and cluster bin packing. Let's take a look at workload right-sizing, for example. So if you build an application, you have to specify resource requests and resource limits for all your workloads that you deploy to a platform like Kubernetes in order to make it efficiently work in the way it's supposed to work. However, it's super complicated to come up with reasonable resource requests and resource limits that actually align with those resources that our application requires while running and while facing load. But there's a solution for that. There's WebAssembly, and WebAssembly addresses a lot of those shortcomings that we as developers deal with when we use containers. And let me quickly guide you through my personal highlights of WebAssembly. First, WebAssembly is portable. We take our source code and we compile it down to WebAssembly. WebAssembly itself, so the resulting binary, is portable across operating systems and across CPU architectures, meaning we don't have to cross-compile anymore. We take our code, compile it down to WebAssembly, and then we can simply throw that distributable across the fence towards an AMD 64 or an ARM 64 machine, it does not matter, because the WebAssembly runtime and underlying WebAssembly system interfaces take care of talking to the native APIs on that particular platform. Second important value add from WebAssembly is small package sizing. There is nothing involved in creating a WebAssembly distributable than our application code. So for example, if we take a Hello World application and compile that down to WebAssembly, the resulting OCI artifact that we can use as distributable unit is less than 300 kilobytes in size. And even for complex applications, we are talking single up to 2-digit megabytes in total size for the entire distributable of our app. WebAssembly, it has been invented for the browser, meaning we have a strict sandboxed environment. And for the first time ever, we as developers can put detailed or precise permissions on our workloads. So without specifying permissions, a WebAssembly module is not able to interact with any resources. If your app has to read the file system, you have to explicitly grant the permission to the app to do so. And the same applies for doing outbound network requests or things like that. So we have a strict isolated sandbox, which allows us to package many workloads on a single machine without fearing that one app could take down another app. The small package size and portability gave us access to an incredible startup performance. So with WebAssembly and Spin, and we will talk about what Spin is in a second, we are able to have cold start times from less than a millisecond. So with that, WebAssembly is able to run in a fast and efficient way and unlock real scale down to zero. So I mentioned Spin, but what is Spin? Spin is a developer tool for building serverless or reactive WebAssembly applications. We call them Spin apps. Spin gives you a CLI with a remarkable developer experience and a workflow that is consistent across all the languages that support WebAssembly. Spin is an open source project that has been contributed to the CNCF. So we filed the application to become an official CNCF project for Spin. The good thing about Spin apps or serverless WebAssembly applications is you can run them everywhere. You can run them on your local machine using the Spin CLI. You can run them in our fully managed cloud service called Fermion Cloud, or you can run them on a Kubernetes distribution. And on Kubernetes, we have two options for running WebAssembly workloads. We have open source SpinKube. Again, this is a project we contributed to the CNCF. And we have a commercial offering called Fermion Platform for Kubernetes, which we will only briefly touch within this presentation. So for the rest of this talk, we will focus on the open source Spin as the developer tool and on open source SpinKube as the foundation that we can deploy to Kubernetes to build a serverless platform. Okay, with that, it's time to jump into a demo. We will now create a Spin app and deploy that to open source SpinKube running on a Kubernetes cluster. Let's jump right into the terminal. I have installed Spin on my machine already in the latest version, and Spin gives me the capability to create WebAssembly workloads using different programming languages. The actual programming language does not matter for the sake of this presentation, so I will go with Rust. Spin allows us to create new projects using templates, and I created a P99 conf template already in advance of the conference to, have something that we can take a look at. So let's move into the live demo folder and let's fire up code to see what we got. So this looks pretty much like a regular Rust crate, like a Rust application. However, there's spin.toml, which is the application manifest. Over here, we can configure all the nitty-gritty details of our application. And you can see in the command section down below here, we can customize which commands will be executed when we ask Spin, for example, to compile our source code down to WebAssembly. All right, let's take a quick look at the implementation. So as you may already guess, this is an HTTP API. We will expose two HTTP endpoints. So callees can send either a HTTP GET or an HTTP POST request to our API, and they will receive back a response. All right, that said, let's go back to the terminal. Let's clean it up and let's run a spin build to compile the Rust code down to WebAssembly. If you do that for the first time, you may recognize it's pulling all the dependencies and compiling them to WebAssembly on my local machine. Finally, we end up with finished building all spin components. So let's clean the terminal, and running the app on the local machine is as simple as doing a spin up. So now my app is running and waiting for incoming requests on port 3000. Let's move over to the next terminal and let's invoke the endpoint. So first let's hit the get endpoint that responds with hello Fermion, and next let's do a curl x posts. So let's send the post request to the second endpoint, and we get back a JSON object with a greeting hello P99 conf. So now that we have the app running, I want to give you a little bit more understanding of how fast WebAssembly is. And to do so, we can send 2000 requests to that get endpoint and check how long Spin requires to process all of them. And that's it, right? As you can see, 99% of those 2000 requests, by the way, all were successful, were able to complete within 9.3 milliseconds. And this is everything running on my local machine. The impressive thing about that performance is that each and every HTTP request results in a cold start. So if a HTTP request hits that port that we are listening, or that Spin in our case is listening to, right? The WebAssembly module will be loaded in memory, it will be instantiated and invoked. Then our code will be, or does some computation, right? It constructs an HTTP response and it sends that back. Once the response is sent back, the entire instance of that WebAssembly application is terminated and destroyed, and the memory is freed up. So there is no shared state between individual HTTP requests. And again, every request results in a cold start. All right, so this is the local experience. And I have prepared a Kubernetes cluster, a single node Kubernetes cluster. So we can do a Kubernetes, give me all the nodes. You can see there's an AKS, so it runs on Azure, but it doesn't matter. It could be on-prem, it could be in your private data center. It could be, it just has to be a regular Kubernetes distribution. So this is a single node Kubernetes cluster with 4 CPUs and 16 gigs of RAM. And we can take Spin apps and distribute them using OCI artifacts. And constructing, so packaging and distributing a Spin app is as easy as doing a Spin registry push, and we have to provide an OCI reference. So I will use TTLSH, which is an ephemeral registry that you can use to store container images or OCI artifacts with a time to live configuration. So this OCI artifact will remain available for for 12 hours. So it takes a second to publish the OCI artifact to the registry, but there we are. So on my Kubernetes cluster, I have deployed open source SpinKube. And SpinKube is the idea to integrate seamlessly with the existing Kubernetes ecosystem. SpinKube brings a containerd shim to your Kubernetes clusters, meaning that there is a secondary runtime besides the default container runtime on your cluster. And whenever we ask Kubernetes to deploy a Spin app, we will just spawn a new WebAssembly or the WebAssembly workload for incoming requests on the underlying Kubernetes node instead of starting or running a container. And this allows us to run way more workflows on the same set of compute resources. So right now we have our OCI artifact in the registry. What we have to do next is we have to create Kubernetes deployment manifests. And again, we can use a spin command there. We can say SpinKube scaffold and again provide the reference to our OCI artifact. And without any further addition, this will just print to standard out. And from here, you can take whatever you want or whatever you're used to use as a deployment vehicle. So you can use kubectl, you can use Helm, or you could go the GitOps direction in order to have an operator deploy your workloads. For the sake of demonstration, I will use kubectl apply over here. So we end up with deploying a P99 conf app to the default namespace. And with that, we can set up a simple port forwarding, for example, kube port forward to the service. As we see, that's called P99 conf. And let's again allocate local port 3000 and forward traffic to port 80 of that service. So now requests to my local port 3000 will be forwarded to port 80 of the P99 conf service running in my Kubernetes cluster. Let's go to the secondary terminal and again execute this HTTP request, and we expect back the same result. And if we now move back to the terminal, we should see that one connection was handled. So the interesting thing is, due to the fact that we are not spawning containers, we can scale super fast and we can provision super fast. So remember, this is a single node Kubernetes cluster, right? With 4 CPUs, 16 gigabytes of RAM. And we are able to run a couple of spin apps, right? If we count them, so we remove the headers and count, we can run 222 workloads and we are still not utilizing all the available compute resources. So if we do a K top node, we can see that we are only using a fraction of the CPU. Well, memory utilization is high right now. That's weird. But we still have enough capacity to deploy even more workloads to this particular Kubernetes cluster. If we check for the underlying pods of the spin apps, we can see that an average workload, and by the way, each app is a unique workload doing a different thing, consisting of a different OCI artifact. So on average, every app is utilizing roughly about 20 megabytes of memory and 1 milli CPU when idle. Obviously, there will be spikes for doing actual computation, but this is how far we can get with SpinKube, because we still have the Kubernetes limitations. Like, for example, the maximum number of pods on this cluster is set to 250, which is the maximum that Azure allows us to do. But I want to give you a sneak peek of Fermion platform for Kubernetes. So let me move to the other cluster. This cluster is using our commercial offering, and we're just using a different way of running the workloads. Fermion Platform for Kubernetes is built on top of open source SpinKube. And with that, we can run roughly 4,000 workloads on the same amount of compute resources and be more efficient. So we are only leveraging 12% of the available CPUs and 27% of the available memory to run those almost 4,000 apps. And this is how a remarkable and an efficient, super dense serverless platform on top of Kubernetes could be built with WebAssembly. Let's move back to the slides and wrap this thing up. So some key takeaways for you. First and most important, WebAssembly is finally a first-class citizen on Kubernetes, allowing you to build serverless platforms, as you saw it a couple of minutes ago, but also allowing you to build architectures that consist of containers and WebAssembly. We have open source Spin, which is the developer tool for you to build serverless or reactive WebAssembly apps using different programming languages. So I was using Rust. You can use JavaScript, TypeScript, Python, whatever, as long as the language is able to compile down to WebAssembly. Open source SpinKube lays the foundation to build platforms on top of Kubernetes for running those serverless WebAssembly workloads, and they integrate seamlessly with whatever's out there in the Kubernetes world. Last but not least, there is Fermion Platform for Kubernetes, which allows you to build high-density platforms. And with that, thank you for your attention. If you have further questions, just reach out and let's have a conversation about WebAssembly on the server and in the cloud. Thank you.